An object tore through our solar system in 2025. Not from the asteroid belt, not from the Kuiper belt, from outside. The third known visitor from interstellar space, 3I Atlas. On July 1st, the Atlas telescope in Rio Hurtado, Chile, picked up something moving at 61 kilometers per second through the galactic plane near Sagittarius. Temporary designation A11PL3Z. Follow-up observations confirmed a hyperbolic orbit with eccentricity 6.139. No solar system object gets a number like that. You're bound by our sun's gravity or you're not. 3I Atlas is not. Its velocity relative to the sun, 57.7 kilometers per second. The highest eccentricity of any interstellar object we have seen. Higher than 1I Oumuamua at 1.2. Higher than 2 I Borisov at 3.4. This thing is moving fast and it came from somewhere else. Perihelion, October 29th, at 1.36 astronomical units, just inside Mars. Inclination 175 degrees. Retrograde. Aligned with the ecliptic plane to within 5 degrees. That alignment matters. The plane where all our planets orbit. The probability of a random interstellar arrival matching that geometry is less than 5%, but here it is. Now, something is about to happen that has never been recorded for an interstellar object. On January 22nd, 2026, at 1300 hours Coordinated Universal Time, Earth will slip almost directly between the Sun and 3I Atlas. The phase angle between the Sun, 3I Atlas axis, and the Sun-Earth axis will reach 0.69 degrees. That is the tightest opposition alignment we have ever achieved with a visitor from another star system. For approximately 1 week, from January 19th through January 26th, that angle stays below 2 degrees. During this window, a phenomenon called the opposition surge becomes measurable. Shadows disappear. Light scatters back at angles that reveal the structure and composition of the dust this object sheds. Avi Loeb at Harvard and Mauro Barbieri published their research note on January 12, 2026 in a Medium post, outlining the geometry and the scientific opportunity. They are calling for coordinated photometric and polarimetric observations across multiple sites. The window is narrow, the magnitude is faint, 16.7 in the V-band, but the data could answer questions we have never been able to ask an interstellar comet before. Medium and verified through the R-Cursive preprint server at 2.601.08624, alongside NASA JPL Horizons trajectory data, updated through January 2026, and peer-reviewed observational papers from astronomy and astrophysics, including the Gran Telescopio Canarias spectroscopic study, published August 2025. Now back to the information. 2 physical mechanisms drive it: shadow hiding and coherent backscatter. Shadow hiding happens when the sun is almost directly behind the observer. Dust grains that normally cast shadows on each other become fully illuminated. No shadows means more reflected light, more brightness. This effect dominates at phase angles above 2 degrees. Below 2 degrees, coherent backscatter kicks in. Light waves traveling through the dust medium interfere constructively, a quantum mechanical spike in brightness. The amplitude and width of this surge depend on 2 things: the albedo of the dust and how the grains are packed. Compact grains produce narrow angular features. Fluffy fractal aggregates produce broader features. Low albedo around 0.03 means carbonaceous material. High albedo between 0.1 and 0.3 means ice fragments. For 3I Atlas, we do not know which it is yet. The January 22nd alignment will tell us. Larger apertures needed for polarimetry. Multiband observations across at least 3 broadband filters. Relative precision near 0.03 magnitudes per data point. Consistent apertures. Proper background subtraction. This is not casual viewing. This is precision measurement during a fleeting window. By January 2027, the magnitude drops to 24. January 2028, magnitude 25. The object fades as it recedes. After this week, we may not get another chance for decades. The tail always points away from the sun, always. Except here. 3I Atlas shows a prominent anti-tail jet extending in the sunward direction. The first Hubble image captured it at an observing angle 10 degrees off the sunward direction. Simple projection geometry means the actual structure is 1 divided by sine of 10 degrees, 5.8 times longer than it appears. The jet is roughly 10 times longer than it is wide, tightly collimated, extending out to 400,000 kilometers from the nucleus. That is the Earth-Moon distance. The latest Hubble image from January 7, 2026, processed by Tony Scarmato using a Larsen-Sekanina rotational gradient filter, reveals a triple jet structure, the dominant sunward antitail, 2 smaller jets equally spaced in angle, not oriented away from the sun. None of this fits standard cometary models. The antitail persists after perihelion. That is the real puzzle. 3I Atlas reached perihelion on October 29th, 2025, At 11:44 Coordinated Universal Time, solar heating was maximum. The sun-facing side during approach became the night side after perihelion because the gravitational deflection was only 16 degrees. The rotation axis of the nucleus appears aligned with the sun to within 7 to 8 degrees based on periodic wobbling detected in the jet structure. Observations from the 2-meter twin telescope at Tidy Observatory across 37 nights between July 2nd and September 5th, 2025, showed the anti-tail jet wobbling every 7 hours 45 minutes. That implies a nucleus rotation period of about 15.5 hours if the jet originates from a single active spot. The rotation axis pointed at the sun before perihelion. After perihelion, the original sun-facing pole is now on the night side, yet the anti-tail persists, still sunward, still collimated. A new study by Loeb and Schermato, published in December 2025, estimates the post-perihelion rotation period at 7.1 hours based on jet orientation changes and brightness variations. Reach these distances. Normal dust grains, 1 micron or smaller, scatter sunlight efficiently but get pushed back fast. 3. I-Atlas sheds particles between 1 and 100 microns, bigger than common dust, heavy enough to resist immediate dispersal but light enough to be dragged by outflowing gas. The mass loss rate estimated from Webb telescope data in late 2025 was 150 kilograms per second. Near perihelion, that could have grown to 500 kilograms per second. The jet is collimated within a cone of about 8 degrees opening angle. That gives a solid angle of 0.06 steradians. Using these numbers, the gas density falls off inversely with the square of distance from the nucleus. Dust particles dragged along by this gas can reach the observed lengths only if they are in that specific size range. Too small and radiation pressure winds, too large and gravity or drag cannot accelerate them enough. The dust is too big to be blown backward. The sunward anti-tail dominates the visual appearance. That is one of the highest carbon dioxide to water ratios measured in any comet. Solar system comets usually show water as the dominant volatile. This object is different. Cyanide detected by the Very Large Telescope on August 14, 2025. Nickel detected on August 18th. Both break off from surface compounds as solar heating increases. Spectroscopic data from the Gran Telescopio Canarias using the OSIRIS Plus camera spectrograph across the near UV and visible wavelengths 3500 to 9200 angstroms showed a red spectral slope similar to 1I Oumuamua, D-type asteroid characteristics, low albedo surface, primitive carbonaceous material. Rotation period derived from light curve analysis, 16.79 hours plus or minus 0.23. Hours based on observations in July 2025. The explanation: sunlight heating small icy grains released from the nucleus, allowing them to vaporize in the surrounding coma even at large heliocentric distances. Before perihelion, ice signatures were strong. After perihelion, ice signatures faded. A rich mix of organic molecules and gas form appeared. Water production increased dramatically. Something beneath the surface was exposed by solar heating near perihelion. How old is this object? Tracing the trajectory backward through the galaxy using Gaia Data Release 3 stellar kinematics, researchers mapped 3I Atlas against over 13 million stars. No stellar flyby within the past 10 million years and 500 parsecs can account for its present trajectory. The strongest perturber, at 0.3 parsecs with a relative velocity of 35 kilometers per second, imparted a velocity. Change of only 5 times 10 to the minus 4 kilometers per second. Essentially nothing. The object has been drifting through the galaxy undisturbed for a very long time. Its velocity components place it in either the Milky Way's thin disk or thick disk. If thick disk, the typical ages of stars in that population range from 7.6 to 14 billion years. That makes 3I Atlas potentially older than the solar system, which formed 4.6 billion years ago. Independent analysis by Astor Taylor and Daryl Seligman in July 2025 estimated 3 to 11 billion years. A third study suggests around 10 billion years based on galactic disk membership and kinematics. If confirmed at the high end, this object witnessed cosmic noon, the peak era of star formation in the universe's history. It carries material from a protoplanetary disk that condensed before our sun ignited. 3I Atlas formed in the outer regions of that system, beyond the carbon dioxide frost line where temperatures dropped below 20 Kelvin. At some point, a close encounter with a giant planet or a passing star flung it into interstellar space. Travel time from its parent system to here, approximately 800 million years. It has been alone for nearly a billion years before arriving at our doorstep. Hubble images from August 20th, 2025, constrained the nucleus diameter between 440 meters and 5.6 kilometers. Estimated mass: over 33 billion tons, assuming a density between 200 and 600 kilograms per cubic meter typical for cometary nuclei. Non-gravitational acceleration detected by positional measurements indicates asymmetric outgassing, acting like small thrusters. This is expected. Comets rarely outgas uniformly, but the magnitude and direction of the acceleration provide clues about active regions on the surface. NASA's Mars Reconnaissance Orbiter data delayed due to the agency's shutdown at that time. Tianwen-1 from CNSA captured images. Juno at Jupiter may attempt observations during the March 16, 2026 flyby at 0.358 astronomical units from Jupiter, but fuel constraints and engine issues make that uncertain. Psyche spacecraft passed 0.302 astronomical units from 3 IATLAS on September 4, 2025. JUICE passed within 0.428 astronomical units on November 4, 2025, in attempted observations, but thermal conditions during inner solar system transit meant data would not reach Earth until February 2026 because the high-gain antenna was needed as a heat shield. Europa Clipper was predicted to pass through the ion tail between October 30th and November 6th, 2025, potentially detecting ion tail signatures and magnetic draping structures in the solar wind. Faint cometary activity. Las Cumbres Observatory, 0.36 meter telescopes at Haleakala, and the 2 meter Falks telescope north provided light curve data showing minimal brightness variation. The light curve was predominantly flat during early observations, indicating a surrounding homogeneous coma. Later variability suggested rotation and possibly active regions becoming visible as the nucleus turned. On December 11, 2025, 3I Atlas passed less than 2 degrees from the half moon. Opposition, 177.6 degrees from the Sun, occurred on January 22, 2026. The comet had been observable at midnight since mid-December 2025, but much fainter than during approach. Magnitude around 13 as of January 10, 2026, located in the constellation Cancer. Now the alignment. January 22nd at 1300 hours UTC. Phase angle 0.69 degrees. Earth almost directly between Sun and comet. The sunward anti-tail will be aimed straight at us. This geometry amplifies backscatter effects. Light reflects directly back toward the source with minimal angular deviation. Measurements taken during this brief window can reveal dust albedo through the surge amplitude. Grain structure through the surge width, carbonaceous or icy, compact or fluffy. Wavelength-dependent photometry across BVR or GRI filters will show if the surge is stronger at shorter wavelengths, a signature of coherent backscatter in fine-grained material. Polarimetric data near minimum phase angle will constrain multiple scattering effects and grain packing density. Coordinated observations from multiple sites improve temporal sampling and mitigate weather gaps. Even partial datasets contribute meaningfully to phase angle behavior characterization. Precision is key. Relative photometry to 0.03 magnitudes. Consistent aperture sizes. Proper background subtraction to avoid contamination from faint background stars or gradients. The comet is faint, 16.7. Close to the limit for moderate-sized amateur telescopes, but well within reach of professional 1-meter class instruments. Exposure times need calibration. Too short and signal-to-noise suffers. Too long and the comet's motion smears the point spread function. Continuous monitoring captures the full surge profile. The rise as Earth approaches the opposition geometry. The peak at minimum phase angle. The decline as Earth moves past. Fitting models to that profile extracts the physical parameters. Shadow hiding dominates the broad surge at angles above 2 degrees. Coherent backscatter creates the sharp spike below 2 degrees. Separating the two components requires dense phase angle sampling. That means multiple observations per night, if possible. From September 2026 through May 2027, 3I Atlas will be observable again when it reaches the orbit of Saturn and beyond. Ground-based facilities can track it out to the orbit of Uranus in late 2027. By September 2027 through the end of 2028, only the largest space telescopes can see it. After that, it fades below detection thresholds. Gone. Back into the darkness between stars. Addition to the stronger dayside jet. For a natural comet, that is plausible. For a technological object, a hypothesis Loeb has not dismissed despite NASA's official stance, the sunward jet might serve as protection against solar wind, coronal mass ejections, or intense sunlight. The anti-tail is marginally opaque based on brightness measurements. Could it act as a shield? Speculation, but the geometry raises the question. 2. Both jets launch from the sun-facing side. The sunward jet extends hundreds of millions of kilometers for 10-micron dust particles based on radiation pressure calculations. Sub-micron particles or gas swept by the solar wind would extend only a few million kilometers sunward before radiation pressure decelerates them, and they turn around quickly, constituting the second jet heading away from the sun. Spectroscopic measurements of velocity profiles from large telescopes like Keck or VLT could distinguish between these interpretations. If both jets show launch from the sun-facing side, The weaker jet would accelerate to increasing recession speed with distance as particles turn around after being slowed by radiation pressure. After perihelion, if the axis did not change orientation, the original sun-facing pole is now on the night side. Yet the anti-tail persists, strong, collimated, sunward. Either a new pocket of ice near the opposite pole activated after perihelion, or something else is driving the outflow. 13 anomalies listed by Loeb in published analyses include the ecliptic alignment, the rotation axis alignment, the anti-tail collimation, the post-perihelion persistence, the large particle sizes, the absence of submicron dust, the high carbon dioxide ratio, the low water to carbon dioxide ratio pre-perihelion, the dramatic shift in composition post-perihelion, the tight jet wobble period, the sustained activity at large heliocentric distances, the spectroscopic signatures of nickel and cyanide, and the age estimate placing it older than the solar system. The 14th anomaly, the rotation axis remaining aligned sunward through perihelion and beyond. The combined probability of the ecliptic alignment and rotation axis alignment occurring by chance is less than 1 in 10,000. Dynamical anomalies were not addressed in the public statements. The focus remained on the natural origin explanation. Data released by NASA and ESA through Hubble, Webb, SphereX, and Mars, orbiters show the anti-tail is not an optical illusion, not a projection effect. Multiple observing angles over several months confirm it is a physical structure. Repeated detections from July through January. The January 7th, 2026. Hubble image processed with the rotational gradient filter removes the circularly symmetric glow around the nucleus, exposing the triple jet structure unambiguously. The anti-tail extends on the order of the Earth-Moon distance. That is not subtle. Dust grain properties differing from solar system comets due to formation in a different stellar environment. All plausible. But none fully explain the tight collimation, the persistence against solar forces, and the sunward orientation sustained for months after perihelion. The data demand mechanisms beyond standard sublimation-driven outgassing. Astronomical units, 53.6 million kilometers. Jupiter's gravity is immense, radiation belts intense, electrically charged environment harsh. If the object passes too close or experiences destabilization, the encounter could disrupt it. Fragmentation is possible. Comet 2, I-Borisov, fragmented in 2019. 3, I-Atlas, shows no signs of structural instability so far, but Jupiter is unforgiving. The jet configuration offers no indication the object is adjusting for that encounter. It continues outbound on its hyperbolic trajectory. After Jupiter, it accelerates away from the solar system, projected to reach the inner Oort cloud region around 2189. By then, over a century away, it will be light years into interstellar space. A moment when our viewing geometry allows measurement of properties that cannot be obtained any other way. The opposition surge is real. The physics, well understood from decades of studying solar system bodies. The moon's brightness increases more than 40% between phase angles of 4 degrees and 0 based on Clementine spacecraft observations. Dwarf planet series observed by the Dawn mission at 0 degrees phase angle showed a surge with amplitude approximately 0.3 magnitudes, corresponding to an enhancement factor of 1.38. The surge half-width at half maximum was 2.8 degrees, dominated by shadow hiding, in a highly porous surface with porosity around 90%. Comet 67. P. Churyumov-Gerasimenko, observed by Rosetta from 2014 to 2016, showed a surge enhanced by dust jets, with an enhancement factor around 1.6 at 649 nanometers. Enceladus shows one of the strongest surges among Saturn's moons, driven by fresh, porous ice and coherent backscatter and fine-grained frost. Europa's leading hemisphere, dominated by clean water ice, displays a sharp surge attributed to coherent effects, with Galileo observations showing an enhancement factor about 1.5 times predicted values when transitioning from 5 degrees to 0 degrees phase angle. 2, I-Borisov, was never observed at phase angles below 16 degrees. 1, I-Oumuamua, showed no dust or gas activity. 3, I-Atlas is active, shedding dust continuously, and the geometry on January 22nd places it at 0.69 degrees phase angle, the closest we have ever come. The surge amplitude will reveal albedo. High albedo means icy fragments retained from the parent protoplanetary disk. Low albedo means carbonaceous material processed through billions of years in interstellar space or thermally altered near the parent star. The surge width will reveal grain structure. Narrow width means compact grains, thermally processed. Broad width means fluffy fractal aggregates, pristine molecular cloud material. Wavelength dependence will separate shadow hiding from coherent backscatter. If the surge is 3 to 4% larger at 0.41 microns than at 1.0 micron, shadow hiding dominates, consistent with the lunar case. If the surge shows strong wavelength dependence with enhancement peaking in the blue, coherent backscatter plays a major role. These signatures are direct evidence of coherent backscatter. Measurements at minimum phase angle during the alignment can confirm or rule out significant coherent contributions. That constrains grain size. Coherent backscatter requires particles with radii similar to the wavelength of incoming light and very high single scattering albedos close to unity. If 3I Atlas dust shows strong coherent backscatter, the grains are fine and highly reflective. If shadow hiding dominates, the grains are larger and possibly darker. How they respond to sudden heating when entering a new stellar system, whether their dust properties differ fundamentally from solar system comets or fall within the same range of parameters. Each interstellar visitor teaches us something about the diversity of planetary systems across the galaxy. 1I Oumuamua taught us that small rocky interstellar objects exist and can exhibit non-gravitational accelerations without visible cometary activity. 2. I Borisov taught us that interstellar comets can resemble solar system comets closely in spectroscopic and photometric properties. 3. I Atlas is teaching us that interstellar comets can be ancient, carbon dioxide rich, and exhibit jet structures that challenge our models. The only near-opposition observation of an interstellar comet we may get for decades. The next interstellar visitor could arrive next year or in 10 years. We do not know. The Vera Rubin Observatory, set to begin operations soon, will discover many more interstellar objects with its deep, wide-field surveys, perhaps a 4I within a few years. Each new visitor is an opportunity, each alignment a fleeting window. ESA's Comet Interceptor mission, planned for launch in the late 2020s, could rendezvous with a future interstellar comet, if discovered with sufficient lead time. Direct sampling, in situ measurements, that would be transformative. But for now, we have 3I Atlas, remote observations, ground-based and space-based telescopes, photometry, spectroscopy, polarimetry, extracting every bit of information the light carries. The scientific community is mobilizing. Observatories across continents are scheduling time, professional and amateur networks coordinating, rapid data sharing to facilitate preliminary analyses during the observation window itself, high-precision photometry, polarimetric monitoring, multiband coverage, temporal sampling dense enough to capture the surge profile. Protocols in place. The goal, maximize the scientific return from this single pass. 3I Atlas will not return. Hyperbolic trajectory, one chance. If the jet is truly as collimated and extended as Hubble images suggest, the opposition surge might reveal internal structure, variations in brightness along the jet length, asymmetries, fragmentation, or discrete emission sources. Spectroscopic observations during the alignment could measure Doppler shifts if the jet material has a velocity component along the line of sight. That velocity tells us ejection speed from the nucleus. Combined with mass loss rates and density profiles, ejection speed constrains the mechanism. Sublimation-driven outflows have characteristic speeds. Rocket exhaust has different speeds. The distinction is measurable. The data are public. NASA, ESA, Hubble, Webb, SphereX, multiple ground-based observatories, all contributing observations. Independent researchers processing the images, running models, publishing findings. The anti-tail is real. The alignment is real. The rotation axis alignment is statistically unlikely. The ecliptic alignment is statistically unlikely. The age estimates place it older than the solar system. These are not fringe claims. These are measurements. The interpretation is where debate exists. Natural comet with unusual properties due to formation in a different environment, or something else. The January 22nd alignment will not answer that question definitively, but it will constrain the range of viable explanations. That implies thermally processed material, compact grains, consistent with a comet that formed close to its parent star or underwent significant heating events during its history. Another scenario, the dust is icy with high albedo between 0.1 and 0.3. The surge is sharp. Coherent backscatter contributes significantly. That implies pristine material, fluffy aggregates, consistent with a comet that formed in the cold outer regions and has been preserved in interstellar space for billions of years. The extended anti-tail with large ice particles, suggested in earlier papers by Loeb and Quito, fits this scenario. Intermediate scenarios exist: mixed composition, dust population with a range of sizes and albedos, layered structure with processed surface and pristine interior. The January observations will narrow the possibilities. Webb might observe depending on target availability and science priorities. Ground-based observatories with apertures from 1 meter up to the 10.4 meter Gran Telescopio Canarias will contribute. SphereX data from the alignment week will be analyzed in the coming months. Every dataset adds constraints. Every measurement reduces uncertainty. By the time 3I Atlas fades beyond detection in late 2028, we will have assembled the most comprehensive dataset ever collected on an interstellar comet. Discovery, approach, perihelion, precession, alignment, Jupiter encounter, departure, 12 to 18 months of continuous observation, dozens of telescopes, hundreds of researchers, thousands of images, petabytes of data. The object will continue outbound, crossing the orbit of Saturn in 2026, Uranus in 2027, Neptune around 2030. Beyond that, interstellar space. No more observations, no more data. The archive will remain. The measurements will be analyzed for years, models refined, theories tested, comparative studies with future interstellar visitors. Each new discovery builds on the last. 3. I-Atlas is the third confirmed interstellar object. The first with detailed multi-wavelength observations across its entire passage. The first with a near-opposition alignment. The first with sustained space-based imaging from Hubble and Webb. The first observed by multiple planetary missions simultaneously. The legacy will be the data. A rare opportunity to probe the physical properties of material formed around another star, to test whether interstellar dust behaves like solar system dust or exhibits fundamental differences, to measure albedo, structure, composition, using techniques refined over decades of planetary science, to apply those techniques to an object that has traveled for hundreds of millions of years across the galaxy, to ask whether the building blocks of planetary systems are universal or diverse, to wonder whether life arose elsewhere under different conditions, different chemistries, different timescales. 3. I-Atlas does not answer those questions, but it provides a piece of the puzzle. One object, one data set, one alignment. Traveler. When the phase angle reaches 0.69 degrees, when the opposition surge amplifies the faint reflected light, when telescopes around the world point toward Cancer and capture photons that left the comet minutes earlier, when the data streams in and the analysis begins, what will the dust tell us? Carbonaceous or icy? Compact or fluffy? Old or ancient? Familiar or alien? The answer is in the light. Pointed at the sun, collimated, persistent, defying easy explanation. The triple jet structure captured on January 7th, the wobble detected in July and August, the rotation axis aligned within 8 degrees, the post-perihelion jet from the night side pole, the large particles resisting radiation pressure, the high carbon dioxide ratio, the dramatic composition shift, the age estimate placing it in the thick disk, 7 to 14 billion years old, the absence of stellar flybys that could alter its trajectory, the alignment with the ecliptic plane to within 5 degrees, the hyperbolic orbit with eccentricity 6.139, the velocity of 57.7 kilometers per second relative to the Sun, the combined probability of the geometric coincidences less than 1 in 10,000. These are the facts. Grain size from coherent backscatter contributions. Composition from spectroscopic follow-up, all of it feeding into models, constraining parameters, narrowing uncertainties, building knowledge. The activity declining as heliocentric distance grows, the magnitude dropping, the signal fading, until one day the last image is captured, the last spectrum recorded, the last data point added to the archive, and 3. I-Atlas disappears, back into the interstellar medium, alone again, carrying its secrets into the void. The near-opposition alignment on January 22nd, 2026, the surge amplitude, the grain structure, the dust composition, the evidence, and when the next interstellar visitor arrives, when 4i is discovered, when the telescopes turn and the observations begin, we will compare 3. I-Atlas and 4i, similarities and differences, patterns and outliers, building a sample, one object at a time, learning what is typical and what is rare, what is universal and what is unique, understanding the diversity of material in the galaxy, the remnants of dead worlds, the building blocks of new ones, the chemistry of planetary systems across billions of years, the story written in dust and ice and light, the only near-opposition observation of an interstellar comet we have, the measurement that tells us whether the dust is carbonaceous or icy, compact or fluffy, whether coherent backscatter contributes or shadow hiding dominates, whether 3. I-Atlas is an outlier or fits within the range we expect, whether its anomalies are artifacts of viewing geometry and composition or signatures of something deeper. The data will speak. On January 22nd, phase angle 0.69 degrees, Earth between Sun and comet, light scattering back, shadows disappearing, the opposition surge rising, telescopes watching, photons counting, the measurement beginning, verifiable, science. The alignment gives us that. 1 week, 1 chance, 1 data set. What the ancient dust from another star system formed perhaps 10 billion years ago, traveling 800 million years across the galaxy, entering our solar system in 2025, passing perihelion in October, aligning with Earth and Sun on January 22nd, 2026, what it reveals when the geometry is perfect and the light comes, straight back. The moment when Earth and Sun and ancient comet line up, and we watch, and we measure, and we learn. January 22nd, 2026, 1300 hours, UTC. Phase angle 0.69 degrees. The opposition surge. The measurement. The answer waiting in the light.